Okay, in the folder for this week, there are all right, there you go. There are three things at the bottom. One of them says limiting reactance notes. That's the thing you picked up on your way in, or if you're remote, you can follow through that way. Or there's also the same handout is as a PDF. You can view it that way too. Either way, it doesn't really make a whole lot of difference. But the PDF has like stuff filled in, so it's all in one shot, and that's not what you got if you're here. And then there's another paper that says limiting reactance, worksheet number 1. So this is some practice that you can do um, for tomorrow, and we'll go over those tomorrow. And then I've got a bunch of other problems for you to practice about like limiting reactance. Okay, so the deal with the s'mores lab is that you've got these ingredients to try to make s'mores. And in a way, like cooking is a lot like doing chemical reactions where you take the ingredients and you try to make some kind of products. I mean, some chemical reactions are decomposition reactions, and there's no issues with like limiting reactants. You're not like going to have one thing run out first if it's a decomposition reaction. But for most chemical equations, there's something that you're going to run out of first. It's something where you're going to like, uh, you know, not have enough to complete the reaction to make as much as you want. So whenever we look at the problem with making s'mores, you have like a limited number of s'mores that you can actually make with the ingredients that you actually have. And it can be the same with any other kind of deal. So the concept of limiting reactants is important because it helps you understand how you end up with a certain amount of quantity of a product that you're looking to end up making. Let me see if I can get this to work again. I don't know why I'm getting like two screens for the same thing. All right. So the deal is, up until now, we've said when you write a chemical equation, in that chemical equation, it tells you the ratio of the reactants and the quantities of products that you get. But in reality, in most chemical equations, you end up with something being limited. Something is the limiting reactant. Something limits how much product you can end up making. It's much like when you have a bunch of graham crackers and a bunch of chocolate and a bunch of marshmallows. You run out of something first. You can make so many total things, and those leftover things are called the excess reactant, the thing that's in excess. And one example is like if you go to burn wood. So if you start a campfire or you light something on fire, the things that you need include the fuel, which is wood, and you also need oxygen. You're not going to run out of oxygen. You've got the oxygen for the entire atmosphere, the whole planet. It's not like, oh, why'd your fire go out? Oh, we ran out of oxygen. That's not what happens. So oftentimes when you think about some common chemical reactions, something is available in unbelievable excess. The oxygen is in excess. What limits the amount of energy you get is the amount of wood. Or like if you drive a car down the road and it runs on gasoline, you've got gasoline and you got the oxygen in the air. You're not going to run out of oxygen in the air. You're going to run out of gas first. Nobody like says, "Oh, my car stalled. Why? Ran out of oxygen." No, you run out of the gas. The gas is the limiting reactant, or like the gasoline is the limiting reactant. The oxygen is what's in excess. So we would call the wood the limiting reactant, and the oxygen is the excess reactant. So here's another example that's a lot like the thing about making s'mores, but this is simpler. You want to make grilled cheese sandwich. Make grilled cheese. You get 2 slices of bread, maybe a slice of cheese, and you end up making this grilled cheese sandwich. And to make the grilled cheese sandwich, you got to have 2 pieces of bread, 1 piece of cheese, and then the sandwich itself would have the equation B2C, 2 pieces of bread, 1 piece of cheese. So let's say you've got 100 slices of bread and you've got 30 slices of cheese. The way that you figured out how many s'mores you could make was to say like, well, this is the question you always ask yourself, how many sandwiches could I make with the amount of bread that I have? So if every sandwich requires 2 slices of bread and you have 100 slices of bread, you've got enough to make 50 sandwiches. But if each sandwich requires 1 slice of cheese and you have 30 slices of cheese, you only have enough cheese to make 30 sandwiches. So you've got the quantity of bread necessary to make 50 sandwiches, but a quantity of cheese necessary to make 30 sandwiches. You are able to make 30 sandwiches. In this case, you would say the cheese is the limiting reactant and the bread is the excess reactant. Because whenever you're finished making your 30 grilled cheese sandwiches, you'll have 30 complete grilled cheese sandwiches, and then you'll have 40 slices of bread left over. And I don't know, you can make toast or something like that, or just get some more cheese, try to make some more sandwiches. That's a lot of grilled cheese sandwiches. I like grilled ham and cheese. I like to grill the ham first too. That way it's not all like cold and gooey. Get a little bit of burn on it. That's good stuff. You make it in your George Foreman grill or on a sandwich or on a frying pan. So the deal is the limiting reactants, what's used up in the reaction, and the limiting reactants what determines how much product is formed. The concept of the excess reactant is that's the reactant that you're gonna have some left over when the reaction is all finished. So in your body, like you take in food and the food is your limiting reactant, but you also take in oxygen and you're not limited by oxygen. You can be limited by oxygen, like, well, drowning is an example of limiting chemical reactions in your body by limiting the amount of oxygen you take in. So try not to drown. And if you stop eating, well, you run out of fuel and your body will, you know, end up stopping. That takes a lot longer, like to starve to death, don't starve to death. So, the difference, this is like on the second page, the limiting reactants get used up. That's how much, that determines the amount of product. The excess reactant doesn't run out. In manufacturing certain chemicals, it is critical that you have exactly the amount of limiting or the amount of each reactant, because you don't want excess reactant because it's like unreacted stuff. In manufacturing drugs, it is critical that the quantities be exactly the same so the pharmaceutical product is as pure as possible. If you have excess one excess reactant, and one of the constituent chemicals that goes to make up the product could actually be poisonous and could contaminate the final pill that you're trying to make. Sometimes with illicit drugs, they'll talk about like there's a bad batch of some kind of drug, and it's as a result that some illicit drug manufacturing that didn't go correctly, and there was an excess reactant that was left in with the final product. That's like what that terminology means. All right, so just the same as putting together sandwiches or putting together s'mores, one of the things runs out first. One of the things you've got excess left over. It can be the same thing with manufacturing. So if you're in the business of like manufacturing a product, you need all the components to all come together in the same place at the same time to finish making your thing. I don't know if you've heard or read, but there's a shortage of a general shortage of microchips around the world for different purposes. And one industry that's actually been hurt pretty bad is automobile manufacturing. Like cars have a lot of chips in them. It's not just like the computer that runs the engine, but there's microchips involved with like the security system, like remote control, like airbag system. And you might be in the business of manufacturing like $50,000 pickup trucks, and you got to shut down production because you're short on a couple little microchips. Part of the reason why chip production has been really limited is there's been a massive demand for electronic devices during the pandemic. Like lots of people buying laptops, people buying like different kinds of gaming systems. People are doing lots of video conferencing. So there's been a huge demand for that kind of stuff. And if you're in the business of manufacturing microchips, and you can make millions and millions and millions of them for, a video game console, you can make a bunch of money that way. But if you make a particular chip for a particular vehicle and there's only like 10,000 of that car made, it's not as profitable. So the car industry has been really struggling to get all the pieces. So here's another example. We're going to try to make a tricycle. So tricycles have components. What do you think? Oh, I just said it. W's for wheel. What about 2P, 2 what? Pedals. S. What part on a tricycle starts with an S? The seat. H. Handlebars. An F. The frame. So to put together a bicycle or tricycle, we're going to need the 3 wheels, and the wheels are a little bit different. 2 of the wheels are the same, one's a little different. So a thing to know is the coefficient tells you the number of individual things you need to make the reaction take place or to manufacture the product. So if you're in the concept of manufacturing or going into business, it doesn't matter what you build or what you assemble. If there's some kind of a product, every product has to have certain numbers of components to make the final thing. And this idea of W3P2SHF means that to make a tricycle, you've got a thing whose formula, in a way, is 3 wheels, 2 pedals, a seat, a handlebar, and a frame. You don't need 2 frames to make a tricycle, and 4 wheels, well, that makes a quadricycle instead of a tricycle. So you got a bunch of different components. All right, so what if you have 50 pedals and everything else is in excess? How many tricycles could you make? $25. You could make 25 tricycles. What if you have 50 seats and you got everything else is in excess? How many tricycles could you make? 50. And if you got 50 pedals and 50 seats, it's just the 25. So the deal is, with every chemical equation, something always runs out first. And the trick is, in this case, what you want to consider is how many of the final product could you make with the numbers of things you start with. Very much like the making the grilled cheese example, that's a little bit simpler. You figure out with each of the ingredients, how many final products could you make? And whenever you consider, if you got 50 pedals and 50 seats, what you're going to run out of first are the pedals. So the pedals are the limiting reactant. You could make 25 bikes. With the 50 seats, you could make 50 trikes, but you can't make 50 trikes because you would run out of the pedals first. So if you're smart, you would order, the correct number, but sometimes things happen. Okay, so here's how it relates to a chemical equation. There's a chemical equation. NH3 is ammonia. Ammonia and oxygen can react to form water and nitrogen monoxide, NO. That equation shows the chemicals that are involved, and um, there are 2 reactants and there are 2 products. There's ammonia, there's oxygen, water, and nitrogen monoxide. To make each reaction go, you need 4 ammonias and 5 oxygens. So the ratio of ammonia to oxygen is 4 to 5. Much like for a tricycle, the ratio of wheels to pedals is 3 to 2. You need 3 wheels for every 2 pedals. For this reaction, you need 4 ammonias, that's the NH3, for every 5 oxygens. And as a result, you would get exactly 6 waters and 4 NOs. Okay. So what if you have 4 moles of ammonia and 5 moles of oxygen? How many moles of nitrogen monoxide would be produced? The first one's easy. So if you got 4 moles of ammonia and 5 moles of oxygen, how many NOs could you make? 4. Because and you would not have anything in excess, and nothing is limiting. Each equation says that for 4 ammonias and 5 oxygens, you get 4 NOs. So with 4 ammonias and 5 oxygens, you get exactly 4 moles of NO. So what if you have 4 moles of NH3 and 20 moles of oxygen? how many NOs do you end up with? Still just 4. So you have the correct quantity of ammonia to make 4 NOs, but you got plenty of oxygen. You got all this extra oxygen left over. The mole ratio in the equation is that for every 4 NH3s, you get 4 NOs. So you've got the right amount of ammonia to make 4 NOs, but you've got excess oxygen, which is okay. In fact, this reaction is a kind of a combustion reaction, but not with a hydrocarbon, but still it's a combustion with something reacting with oxygen. So what if you have 8 moles of NH3, and it seems like you got a whole bunch of oxygen? Yeah, you get 8 moles of NO2 or NO. You could set it up as a mole ratio. So we're going to do that. I'll show you about like writing the mole ratio, but basically you're going to take the quantity of each of the reactants, use a mole ratio to relate it to the quantity of one of the products. It doesn't really matter which of the products, but you'd get 8 moles of NO, because for any amount of NH3, you get the same amount of NO. If we have 4 NH3s, we get 4 NOs. If we have 8 NH3s, you get 8 NOs. If you had 8 moles of NH3, you would only need 10 moles of oxygen, but we've got 20 moles of oxygen, so there's still plenty of oxygen. In all these cases, the ammonia is the limiting reactant, and we've got plenty of oxygen. The quantity of NO you make depends upon how much NH3, but in all 3 of those cases, you had plenty of oxygen to be able to use up all the ammonia. Okay. No, this is not going forward. All right, so there's some other things that are true. These are just some extra things you can read about. If you know the limiting reactant is like some given quantity. That is how you determine how much product you make. So for instance, if you're like, oh, I got all the bread in the world, but I got 30 slices of cheese, the amount of cheese determines how much product you end up making. If you don't know which reactant is limiting, if it's not obvious, you got to calculate which of the products or which of the reactants would give you the least amount of product, and that becomes the limiting reactant. So the reactant that runs out first is the one that makes the smallest amount of product. In the activity with the s'mores, you found that you could make 5 s'mores because one of the reactants, one of the ingredients runs out first. Whichever ingredient or reactant runs out first is the limiting reactant. That's all that you end up making. Okay, so some things that are really important. Like we've worked through all these concepts throughout the year. Uh, Actually, one thing that's more fundamental than making sure the equation is balanced is you got to have all the chemicals written correctly. But you've got to have a balanced equation. When you balance the equation and you put coefficients in front of the chemical, that tells you what the ratio of the chemicals is going to be. And if the equation is not balanced correctly, then you have the wrong ratio. So for instance, if you're like, I'm making grilled cheese sandwiches, I need bread and I need cheese. If you say for every 1 slice of bread, I need 1 piece of cheese, that'd be like an open faced grilled cheese. I guess you could do that. You know what I mean? Like just if you flipped it over, like the cheese would then stick or burn in the pan. You kind of need to have the cheese on the other side. Oh, you gotta have butter too. Get some butter on there. That's what gets you the nice golden brown. But the equation has to be balanced. And then for each of the reactants, you want to calculate how much product you get. We're going to do a couple like specific examples in just a second here. So for each of the reactants, calculate how much product you would end up with. Just like if you're making s'mores or if you're making grilled cheese sandwiches or you're putting together tricycles. I'm down with tricycles. I have a bunch of tricycles. How many do I have? Maybe like 6. That's not too many. I like collect and restore and build bicycles. I have tricycles too. And then the deal is that whichever of the products is in the smallest quantity, the limiting reactant is the one that makes the smallest quantity of product, and the quantity of product that you calculate based upon the limiting reactant tells you exactly how much product you end up with. So just like when we're like, hey, you got this much cheese and this much bread, how many grilled cheese sandwiches can you make? Not only do you run out of one reactant or one ingredient first, but the amount of product that you calculate with whichever the ingredient you run out first is the quantity of product you actually finally end up with. The most important thing is to relate quantities, and those quantities are molar quantities, not just masses. So the thing about the s'mores is, if you know how much a bag of marshmallows weighs, the weight of the bag of marshmallows isn't that instructive. It's not that informative. If you know how much a single marshmallow weighs, then by dividing the mass of the bag of marshmallows by how much each marshmallow weighs, gets you a number of marshmallows, because the number of marshmallows then determines how many s'mores you can make. You can't just relate the masses of the reactants. You've got to relate the quantities, the molar quantities. So just the same as like anytime I said, hey, we gotta, convert to moles first. One of the issues with converting to moles first is that, hold on, that's not right. I gotta get to this thing. When you convert to moles first, that gives you a relative quantity that you can work with. Okay, so let me get, I gotta copy a thing so I can put it on this other thing. Example 2. Okay, so there's 2 examples we'll do, and then do some other ones for practice. Let me get rid of that program, get my 855. Okay, that's the one I'm looking for. This, and then one more page. All right, so here's that same chemical equation that we used whenever we did like quantities. So this equation says that we're going to take, to make the reaction happen, you have 4 moles of ammonia, 5 moles of oxygen gas, get you 6 moles of H2O and 4 NOs. The question is, how much of this NO are we going to make if we have 20 grams of ammonia and 30 grams of oxygen? Now, the equation says that for every 4 moles of ammonia and 5 moles of oxygen, we get 4 moles of NO. But these quantities, grams of ammonia and grams of oxygen, you don't know what the quantity of the chemicals is. So the first thing you want to do is like convert those into moles, get them into a molar quantity. So what I mean by that is if you got 20 grams of NH3, you can convert that into a quantity in moles. For every 1 mole of NH3, it has a certain mass. You got to get yourself a periodic table and you got to find the masses. So let's see. I think it's just 14 and 1.01 on your table. Oh, 14.01 and 1.01. So for ammonia, you got 1 N and 3 H's. Nitrogen is 14.01. Hydrogen is 1.01. So that's 14.01 and 3.03. So when you add up the mass of 1 nitrogen and 3 hydrogen, you get 17.04. That's in grams per mole. So 20 grams of ammonia divided by 17.0 grams gets you a number of moles of ammonia. 20 divided by 17.04. That's 1.17 mole of ammonia. We can do the same thing with the amount of oxygen. So you got 5 moles of oxygen, or 30 grams of oxygen. I'm going to put that over here. So 30 grams of oxygen, you can convert that into moles. For every oxygen has a mass of 16 grams per mole, but it's O2. So the formula mass is 32.00 grams per mole. So 30 grams of oxygen is going to be just shy of a mole, 0.9375. So like always, 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 if you've got a number of molecules, a mass in grams, a volume of a gas in liters, convert it into moles. Just get it into moles. Find the formula mass, convert it into moles. Now, in this equation, it looks like for every 4 ammonias, we need 5 oxygens. So we actually need a greater quantity of oxygen than ammonia. And if you look at the quantities that I just calculated, 1.17 mole of ammonia and 0.9375 mole of oxygen, we actually have a greater quantity of ammonia than we have oxygen. The equation says you need more oxygen than you need ammonia. So it looks like we can already figure out what the limiting reactant is going to be. It looks like oxygen is actually going to limit the amount of product we get, because since you need more oxygen as a quantity in moles than ammonia, we have less oxygen than ammonia. But here's what you want to do. You want to convert each of these quantities for the reactants, moles of ammonia and moles of oxygen, into the number of moles of NO that you would get. So whenever you're working with like integer quantities, like numbers of pedals for a tricycle or number of slices of cheese, they're nice whole number quantities. Oftentimes with chemicals, these quantities aren't nice whole numbers. 1.17, 0.9375, they're not whole numbers. But what you can do is for each of the two chemicals, convert from the quantity in moles of ammonia into the number of moles of NO. So I'm going to write 1.17 mole of NH3 and then use a mole ratio. In the equation, for every 4 moles of NH3, I get 4 moles of NO. So with 1.17 mole of ammonia, you would be able to make 1.17 mole of the NO. With the amount of oxygen you have, if I write the 0.9375 mole of oxygen, when you use a mole ratio from the equation now, in the equation for every 5 oxygen, for every 5 moles of oxygen, you get 4 moles of NO. Now the math is 0.9375 times 4 divided by 5, 0.75. Okay, so just like making s'mores, just like making grilled cheese sandwiches, just like making tricycles, with each of the reactants or with each of the ingredients or components, you figure out how many of the product you could make, and whichever of the two chemicals, in this case, makes the least amount of product, that is the limiting reactant. So with 20 grams of ammonia, the way to look at it is 20 grams of ammonia makes 1.17 mole of NO, but 30 grams of oxygen only makes 0.75 mole of NO. That means that oxygen is the limiting reactant. This O2 is limiting, and the ammonia, that's the excess. The actual amount of NO you make is 0.75 mole. And what we want to know is how many grams do we end up with? So this 0.75 mole of NO, you can then convert that into grams. 0.75 mole of NO, and use the formula mass. Every mole of NO, that's going to have a mass of I guess 30.01 grams. 22.5. That's actually a lot of steps, but that's conceptually what you want to do. You've got to first get the mass into moles for each of the chemicals, and then convert numbers of moles of each of the reactants into moles of product. And then whichever of the reactants has the smallest molar quantity, that then determines the mass of the product you would end up with. But there's another way to do it. And let's see. Oh, at the bottom, that page, that's actually wrong. Where it says how many grams of oxygen are formed, it shouldn't say how many grams of oxygen are formed. It should say how many grams of NO are formed, because we don't form oxygen. The mass of NO that's formed is 22.5. So let me show you a different way to think about it. This is actually the faster way, but it incorporates all the steps into one. And that's to, hold on, let me get down to this last page. Oh, that's weird. The other way to think about it is, I still have the other one on the other page. I'm just going to erase this to give me more space. What you're really trying to do is, if we're trying to figure out a mass of NO that's produced, if we have masses of each of these two reactants, another way to do the problem is to just convert like grams of NH3 to grams of NO, and convert from a mass in grams of NH3 or oxygen into a mass in grams of NO. Do each of those two problems. And when you do each of those two problems, you will find that the mass of NO that you produce will be smaller for one of the two chemicals. So show it to you this way. This is what I do. It's a little bit faster, but you have to understand how each of the steps relates to figuring out limiting reactants. If I start with the 20 grams of NH3, I can first convert that from grams into moles using the formula mass. And that's 17.04 grams of NH3 is 1 mole of NH3. So I've converted from grams of ammonia into moles of ammonia, because the first thing you always do when you have a mass is convert it into moles. And then in the chemical equation, there's a mole ratio. For every 4 NH3, I get 4 NOs. So I can right beside that have another ratio. For every 4 moles of NH3, I get 4 moles of NO. And because I want to know how much mass of NO I form, I can then convert from moles of NO into a mass. So that's, is it 16? Yeah, 30.01 grams. So the first thing is to convert from grams to moles, and then use a mole ratio to relate the quantities, and then finally convert from moles to grams. And if you do that, you're going to get a mass. It's a mass of NO you could produce if you had 20 grams of ammonia. So 20 times 17.04, well, times 4 divided by 4 is the same as 1 times 30.01. Oops, that's got to be divided by there. Divided by, this is 35.2, like about 35.2 grams. If you repeat the exact same thing with the oxygen, with 30 grams of oxygen, the first thing is the formula mass. Convert from mass to moles. 32 grams of oxygen is the mass for 1 mole of oxygen. And then the mole ratio is for every 5 oxygen, I get 4 ammonias. Let me make that smaller. There we go. For every 5 mole of oxygen, I get 4 mole of NO. And then the last conversion factor is exactly the same. (30 divided by 32 times 4 divided by 5 times 30.01. So what's actually kind of faster to do is just take the mass of each of the reactants and figure out what mass of product you would get if you had an unlimited amount of the other reactant. So when I convert from grams of ammonia to grams of NO, you could make 35 grams of NO with the amount of ammonia. But with 30 grams of oxygen, you can only make 22.5 grams of NO. So this is the actual amount of product. This is the amount of the product you get. Just like when you have ingredients, you're going to have so much to make the final product based upon each of the initial things. And that means that oxygen is the limiting reactant. It's exactly the same answer. Like back here in multiple steps, I got 22.5, same 22.5. So usually what you do is just say, well, all right, I know how much mass or what volume or the number of molecules of all these reactants I got. Take that quantity of each of the reactants and do the whole problem to figure out the mass of the product you'd end up with, and whichever mass of the product you end up with is the least, that's how much you actually get. So if you actually took 20 grams of ammonia and you had 30 grams of oxygen, and ammonia burns in the presence of oxygen at high temperature, you actually get those products, and the amount of product you get is 22.5 grams of NO, and you'd have some ammonia left over. You'd run out of oxygen first, and the ammonia, the NH3, the ammonia would be like a little bit left over. So you'd end up with a mix of ammonia, water, and NO. That would be the final thing you'd arrive at. All right, so there's one more example. This one, so aluminum and HCl, you make aluminum chloride and hydrogen. We did this reaction. You might take some metal and some acid, react them together. At some point, the bubbling will stop, and you'll have some kind of product made, and you'll either have aluminum left over, or you'll have some hydrochloric acid left over. So you want to figure out what mass of hydrogen is made based upon some mass of aluminum and HCl. So all you really got to do is start with this mass of aluminum. I'm just going to take 25 grams of aluminum, first convert it to moles. Every mole of aluminum has a mass of 26.98 grams. And then the next thing, because we're trying to figure out the mass of hydrogen that's made, you need a mole ratio. And in the chemical equation, for every 2 mole of aluminum, that's the coefficient in front of the aluminum, you get 3 mole of hydrogen. And because we're trying to figure out the mass of hydrogen, then you just use the formula mass for hydrogen. Every mole of hydrogen has a mass of 2.02 grams. That's the formula mass on the periodic table. 25 divided by 26.98 times 3 divided by 2 times 2.02. We have really only 2 significant figures here, so you'd get 2.8 grams of hydrogen with 25 grams of aluminum. Now, 90 grams of HCl, that's a little bit tricky because usually HCl is hydrochloric acid as a solution, so we actually care about a concentration, but if that were the mass of the hydrogen chloride gas that goes to make hydrochloric acid, it's a valid thing to write, but it's just a little peculiar. But you don't know about concentration yet. We got to get to that. HCl is going to be 36.46. The mole ratio is different because for every 6 HCl, we get 3 mole of H2, but the last is exactly the same, 2.02 grams of hydrogen, a mole of hydrogen, 90 divided by 36.46 times 3 divided by 6 times 2.02, 2.5. So it turns out this is the actual quantity of product you get. HCl is limiting, and the aluminum is excess. Okay, now here's a very important conceptual thing you gotta get. When you first look at the problem and you're like, I got 25 grams of aluminum, I got 90 grams of HCl. At first you're like, all right, I got way more HCl. I'm gonna be able to make as much stuff as the aluminum limits the reaction. So although you've got less mass of aluminum, there are two differences. One, the formula mass for aluminum is different than HCl, and the mole ratio of aluminum to hydrogen and HCl to hydrogen are different. So you can't just look at it. You can't just be like, well, I got less mass of aluminum. Of course that runs out first. That's not true. In fact, in this equation, with those quantities, you run out of hydrochloric acid first because you actually need 3 times as many HCl's as aluminum to make the reaction go, and HCl has a higher mass than aluminum does. So there's a couple to practice there. One is like to make up a thing about relating relative quantities to manufacture something or cook something or whatever. And then on the back, there's another one with calculating relative quantities. If you're remote in the, let's see, new share, this screen. If you're remote, it's this last thing. It says HC Honest Chemistry Limiting Reactants Worksheet 1. So we're going to do a bunch more of these. This first one is good practice. We'll go over this tomorrow at the beginning of class. Tomorrow is Thursday. Thursday is the last day of the week this week for you guys.